Hello, my name is Shin. Here is a description of the method for dealing with variance that was published by Jujutsu Hiransia in Japan. In this case, I compared the existing design methods using probability statistics and the methods for dealing with variance, and compared their accuracy in simulations using random numbers. In design using general probability statistics, the parameters that indicate the performance and reliability of a product in the state of market use are estimated as the mean and variance of a population. The designers then make a judgment as to whether or not the product satisfies the desired performance and reliability. When using standard deviation as the variance, it is assumed that the variance follows a normal distribution, and the portion that differs from the actual distribution shape is an error. In dealing with variance, instead of approximating the variance with a functional distribution such as a normal distribution, the actual distribution shape is determined for each variance factor, and the distribution shape of the parameters of the calculation results that indicate performance and reliability is obtained. I propose to find the probability that it satisfies the target in a rigorous manner. Furthermore, I explain how sampling can be used to obtain an accurate population distribution with relatively small amounts of data in order to understand the distribution. When determining a population distribution by sampling, the number of samples required depends on the structure of the population. Populations used in probability statistics can be classified into two types, which can be distinguished to enable a prospective design. One is a population such as a market survey or a trend study, where the overall trend can be accurately estimated with a relatively small number of samples even when sampling randomly, which is the case for a single source of variance. The second is a population that includes multiple independent sources of variance, such as product or service quality, which have a complex structure. In the latter case, since the population has a complex structure, random sampling may not provide enough information even for a large sample, and the shape of the distribution may not be stable. On the next page, I will explain the difference between a simple population and a complex population. On the following pages, I will compare the existing method and the method proposed in the method for dealing with variability to clarify the number of samples required and the accuracy of the generated distribution when obtaining the distribution for the complex population in 2. The top row of this figure shows the simple population in 1 and the bottom row shows the complex population in 2. To use an analogy with dimensional design. In the case of 1, where the function is determined by a single dimension, the quality is determined by the shape of the distribution of data arranged on a single parameter. Therefore, an accurate distribution of the population can be obtained with a small number of randomly selected samples. 2 is the case where the function is determined by the sum of several dimensions. If, for example, the quality is determined by the effect of only 3 independent parameters, the data must fill a 3-dimensional space. Therefore, when sampling randomly from a population, in case 1, the variance can be grasped with a small number of samples, but in case 2, the same sampling can be done with a small number of samples. In 2, similar sampling will not provide an accurate distribution. Even a large sample may not be sufficient. The method for dealing with variance provides an environment in which the distribution of each variance factor can be ascertained and the distribution of the combined population of these factors can be obtained exactly. The same can be done with the conventional method using the Monte Carlo method, and if it is the mean or variance of a population, it can be obtained with high precision. However, the error can be magnified when determining the shape of the distribution. And the difference is explained later in this section. The top row shows the true distribution of the variance factor and the population. Suppose I include multiple data following the multiple distributions shown here. Suppose I include 3 variance factors, each as a dimension of a component, and that the sum of the 3 is a parameter of the quality of the population of products. The sum of the distributions is the true value of the population distribution. The middle row shows the data generated from the distribution. Generate random numbers according to the distribution of the 3 sources of variation and calculate the sum of those random numbers one by one. The kernel distribution of the summed data is the distribution of the population. The random numbers are varied from 50 to 100,000 to see how the error varies. This is done by generating probabilistically varied values according to the distribution of the 3 sources of variance, and computing the distribution of the calculation results. This is the well-known Monte Carlo method. This is equivalent to creating a distribution from data randomly sampled directly from the post-assembly product population. The bottom row shows the distribution generated from the data. The kernel distribution is generated from the random numbers generated in the middle row. And the distribution of the sum of these distributions is obtained by distribution calculation, which is the method proposed in the method for dealing with variance. The distribution calculation is mentioned in the movie of the paper, and the detailed algorithm is explained in detail in the book. On the next page, I compare the errors when the number of random numbers generated is varied from 50 to 100,000. With the difference between the distribution of true values in the upper row and the distribution of the population in the middle row as comparison A. And the difference between the distribution of the population in the lower row as comparison B. The graph in the center lays out the errors for comparison A of the Monte Carlo method and comparison B of the distribution calculation. The horizontal axis shows the change in the number of random numbers from 50 to 100,000, and is shown in logarithmic scale. The error is the sum of the absolute values of the deviations from the true value of the distribution, i.e., the area of deviation. The upper orange line shows the error of the Monte Carlo method, the lower blue line shows the error of the distribution calculation, and the lower blue line shows the error of the distribution calculation. The gray pull-out lines from the top and bottom show a graph of the distribution at the points on which the error is based. In the upper graph, the blue line is the distribution of true values and the orange line is the distribution of the result of the Monte Carlo method. In the lower graph, the blue line is the distribution of true values and the orange line is the distribution of the result of the distribution calculation. 3 cases with 50 or 200, 2,000, and 100,000 random numbers are included, respectively. The errors are about half those of the Monte Carlo method for the distribution calculation and less than half those of the Monte Carlo method for the number of samples. The reason for this is that the Monte Carlo method calculates the probability of each combination of factors at the time of sampling by random sampling, whereas the distribution method calculates the probability of each combination by random sampling by random sampling. The distributional calculation generates a distribution that strictly reflects the probability value of each combination. As described above, the distribution calculation can generate a highly accurate distribution with fewer samples than existing methods. Of course, if a method that assumes a normal distribution, such as standard deviation, is used, the error will be even larger. Conclusions. The method for dealing with variance is able to obtain the distribution shape of a population with high accuracy with a small number of samplings compared to existing methods. I believe that the more complex the structure of the population, such as software, hardware, and systems to be designed, the more accurate the method is compared to existing methods. By accurately determining the population distribution as described above, it is possible to use the various judgment indicators using the distribution as explained in the other videos, and to improve the quality of design and manufacturing. I believe that this will improve the quality of design and manufacturing. In addition to percentiles, the judgment indicators built into the tool can be used to compare, approach, and balance distributions to obtain exact probability values. That concludes the video. Here is a link to the site where the tools for using the method for dealing with variance are located and the site where the book is available for sale. Thank you very much.